Okay, great. Can you hear me?
Yes. And we
Okay,
cannot hear
wonderful.
your washing machine, so perfect.
Yeah, okay, good. Thank you. So thank you very much for the invitation to speak. I appreciate your patience. Um, I'm unfortunately have not been able to be at many of the talks this week. I had another previous promise that I was going to be at something, but I'm very excited about this science. I think this is wonderful, and it sounds like you guys have had an excellent week. So in particular, today I want to talk about the nuclear physics input for neutron star mergers. And I hope I will convince you by the end of this talk that multi-messenger astronomy really needs nuclear physics. But also the reverse is true, that nuclear astrophysics really needs multi-messenger astronomy to answer the kinds of questions and to really understand how strongly interacting matter works. So we'll see how this goes. I want to acknowledge my excellent collaborators for the particular work that, I'll talk about today. In particular, several people from the University of Tennessee, my graduate students, Saeed Roy, Anik Hassan, my postdoc Zidu Lin, and my current undergraduates, Jesse and Hema. And of course, many other excellent collaborators around the world, which you all know. So just in terms of outline, I'm going to talk about multi-messenger inference for the equation of state and the mass radius curve. So some results that we published last year, and then talk about adding neutron star cooling data and why one would do that. And then the real nuclear physics input for neutron star mergers. We have new equation of state tables. I view these as improvements on the SFHO and SFHX that were published 9 years ago now. And then I want to talk about NP3M and what we're doing there and what our NP3M fellows are doing. So first of all, what we did last year is combine GW 170817 and several electromagnetic observations, including those from, for example, NICER, to obtain constraints on the neutron star mass radius relation and the equation of state of dense matter. I'm sure you guys have talked about this week, and we'll hear more from Jocelyn and Jim after my talk. And my apologies, I'll have to leave right before that. So I'm sorry about that. But in any case, this is a program of just using Bayesian inference plus the TOV equations plus MCMC, which we've been doing for, which we started back 12 years ago now. And so there are a couple of things about this particular work which I think are novel. One is we have few additional assumptions on the equation of state. That was my cat. Of course, not the washing machine. Where am I? Okay. The advertisements about this particular paper, we don't, for example, assume differentiability of the equation of the relationship between pressure and energy density. I should say that for this part of the talk, when I'm thinking about the equation of state, I'm thinking particularly about the relationship between pressure and energy density at zero temperature. So in some sense, that's only part of the equation of state, but this is the part which we can get from the pre-merger signal through for example, the tidal deformability. So we also attempted to test for unknown systematic uncertainties. The electromagnetic data is a little bit more complicated and a little bit more messy than the gravitational wave data. And so we tried to look for so-called unknown unknowns, and we didn't find any. And so that I think is interesting and important. We also tested the variation with the maximum mass. And so you see the results here for these are sets of posterior distributions for our mass radius curve, which I'll talk about a little bit more in detail about in a couple of slides. However, I want to take a step back before I talk about the detailed results and think about how our results fit in with what else is in the literature, or what else was in the literature at the time that this publication was completed last year. So if you think about the radius of a 1.4 solar mass neutron star, and you ask, what are the various, bounds, the confidence limits, you see there's a whole range of results, okay? And as some of the range of results you can attribute to just the fact that they're using different input data. Some of them just, purely GW170817. Some have information about the merger remnant. There are different amounts of electromagnetic data from different sources. But one of the things that you see is even for across works that are using the same data set, they're getting different results. And so what should we make this? What does this mean? And so in the context of Bayesian inference, of course, the analysis technique was also the same, and in some combination, something similar to Bayes plus TOV plus MCMC. But fundamentally, these differences are a result from different prior distributions. And this is not particularly surprising to us. In some sense, the constraint that GW170817 provided on, for example, the neutron star tidal deformability, this is one data point, right? So we're trying to constrain a curve from one data point. This is a very under-constrained situation. Of course, LIGO and Virgo, they measure the strain over many times, right? So there's a lot of work that goes into many data points, but these data points are correlated. And vis-a-vis neutron star structure, this appears like just as if it's only one data point. So of course, LIGO, we are excited about future gravitational wave observations, but this is where we are now. So thinking about the results of this particular paper in that context. So now I can explain. So the different rows represent different data sets. Okay, so there are 4 different data sets. Mostly, I'll just focus on the bottom 2 panels, which, you can think of the bottom row, which is basically all the data put together. And the different columns represent different prior choices. And so you can see that there's certainly a qualitative and quantitative difference in the mass radius relation depending on what your prior distribution is. And not only that, but there is a real physical origin of this prior variation from strong interaction physics. It's just the question of whether or not there's a phase transition, in particular, a phase transition, just above the saturation density, where just above maybe twice, maybe 3 times the saturation density. So this is the kind of thing that really changes the shape of this mass radius relation. This is just part of your prior distribution. We don't know. And because of this uncertainty, 1 and 2 sigma contours may vary by half a kilometer or more, depending on where, this is just thinking about some horizontal line across this, right? A plot, depending on what mass you choose, okay, the left panel and right panel change by half a kilometer. And the posterior radius distribution, even near the peak, varies by a factor of few. Of course, the posterior far away from the peak always varies significantly, but even near the peak, there's a significant variation. And so one of the things that I think is important about this work is simply the way we look at it, and that we're trying to be as honest as possible with regard to the uncertainties in our posterior distribution, without stating them as fact. So what is the solution to this quandary? Well, I'm a theorist. I would love to tell you that I have some grand theory that will tell you the answer to life, the universe, and everything, but basically it's just more data. And this is one of the things that makes this field exciting, is that eventually gravitational wave observations will determine the pressure energy density relation. I think, there are it seems to me that there are a lot of solutions in the literature which suggest, better parameterizations, better prior distributions. But I think these are fundamentally sort of sidestepping the real problem. Yes, it's good to have a good parameterization, but that doesn't really fix the problem. The problem can't be fixed by doing a better prior, because the prior is the problem. The problem can only be fixed by observing more mergers. And so I'm really excited about doing that. With regard to the equation of state, of course, the relationship between pressure and energy density at t equals 0, as I mentioned before, is only, in some sense, a very small part of the equation of state and a small part of what we're interested in the nuclear physics side. We want to know, are neutron stars really neutron stars? Are they mostly a little protons, a lot protons? How many protons are there? And how do these degrees of freedom depend on finite temperature, and what happens when you squish them? Transport properties such as neutrino cross sections and superfluidity. So all of that science we would like to know, in part because it tells us more about QCD. So in line with the new data paradigm, I want to talk about thermal emission from neutron stars, which has been discussed in the literature for several decades now. Basically, the idea is that if a neutron star is by itself, after only a decade, most of the interior is isothermal. And then the temperature evolution is very simple. For an isothermal object, the time derivative of the temperature is just related to the specific heat and the luminosity. And so be it from neutrinos or photons. And so what you see, these colored bands represent theoretical cooling curves, the temperature. So you see a neutrino dominated regime where the neutrino luminosity is larger than the photon luminosity, and then a photon dominated regime where this term is larger than this other one. And so then you see the observations here given by these error boxes. So the basic idea is just, again, you're sort of connecting the dots. Instead of on the mass radius plane, now we're connecting dots on the luminosity time plane. Okay, we can't observe these stars for millions of years, but if we pick many stars and observe them at different ages, then maybe we can learn something. Of course, the luminosity is can be approximately determined by just looking at these objects with an X-ray satellite. The age is a little more difficult. One thing you can do is take them from association with the supernova remnant. This is a particular interesting neutron star, which is not in our data set, but the picture is cool. And so the neutron star here you see speeding away from its original supernova remnant. I think this is the cannonball pulsar or something. So why are we interested in this particular data set? Exactly because it helps us connect to the other things about the interactions between neutrons and protons. For this particular work, we assumed only neutrons and protons, which is a strong assumption, but this is where we are at the time. This tells us about the composition, neutron superfluidity, and proton superconductivity, which also impact the neutrino emissivities, as we'll see here on the next slide. So what were our early results from a couple of years ago? We're adapting this work now, but the early results was that the proton fraction, in the center of the star, the number of protons per baryon, is larger than about 10%. And this is critical because it means, especially for high mass stars, it means they can quickly decay quickly cool. They can emit neutrinos via beta decay. On the other hand, this is a problem because we don't observe a lot of cold neutron stars. The neutron stars actually in this data set are rather warm up here rather than cold down here. And so we have to explain this, and the explanation is that neutron superfluidity pervades the star. And So I'll explain. The theoretical models, unfortunately, computing this critical temperature of the neutron superfluid in QCD is extremely difficult and very model dependent. So we chose some simple phenomenological Gaussian form, which has three parameters: this coefficient, the centroid, and the width of this Gaussian. And so this forms the critical temperature. And what we found, this is a plot of the posterior in this funny nuclear physics units of inverse femtometers. But this delta KFN here is the largest thing around, and that's the width of this distribution. So it turns out that this neutron superfluid is almost everywhere in the star. And so the important thing about what neutron superfluidity does is it quenches beta decay. And so it explains that neutron stars, which are light, cool slowly because superfluidity prevents them from doing so, but neutron stars, which are heavy, cool quickly because of beta decay. And that's the basic picture, which is sort of emerging. And we're working on updating this result. So now we've talked about what we can learn about nuclear physics from multi-messenger observations. I want to go the other way. I want to think in particular about the post-merger signal. Obviously, there's a lot of interest in trying to understand neutron stars and what they're made of due to the post-merger signal, but analyzing this will require the numerical simulations of binary neutron star mergers. We've heard about that already this morning, and at least from Francois and David earlier this week, and I would guess others as well. And my claim is, sounds sort of pessimistic from the start, is to say, look, the current nuclear physics input in these simulations is not sufficient to accurately describe the post-merger simulation or the post-merger remnant, nor to properly quantify the uncertainties. This is where we are. This is hard work. We need a lot of excellent people, and we need money to do this. But at the same time, acknowledging that it's hard, we're making progress on both fronts. And so I want to describe at least some of my group's efforts in this direction. So as I mentioned, we've created new equation of state tables this is Xingfu Du and myself and Jeremy Holt, and we have a couple of publications. So what is at the minimum needed? Well, you need a table of all of the thermodynamic quantities, the pressure, the energy, and the entropy, as a function of three variables: the number of baryons per unit volume, the number of electrons per baryon, and then the temperature. And so canonically, most equation of state tables, including, for example, SFHO, take one particular model of neutrons and protons and just extrapolate them everywhere. Even though we know that the particular Lagrangian on which SFHO was built does not really apply everywhere in this three-dimensional space. So in this new work, we attempted to address this by sort of patching together, quilting different models together to get a supermodel, which describes matter properly in all the various physical regimes. And so I want to talk a little bit about these 5 physical regimes and where their experimental and observational constraints are. So first, isospin symmetric, that is y equals a half, equal numbers of neutrons and protons matter near the density, saturation density, the so-called, this is the density in the center of a nucleus. Well, of course, this is very well represented by laboratory nuclei and measured at places like FRIB. And so the nuclei collaboration has given us models which fit this data. And so we take advantage of that input. Now for neutron-rich matter, obviously nuclei always have protons around, but at this same density, nuclear theory does extremely good job of describing the equation of state. especially at zero temperature. And so Stefano Gandolfi, for example, and Joe Carlson and Sanjay Reddy have a publication which describes this. And there's a lot, of course, there's a lot of work from, for example, from Darmstadt, from Schwenk et al. On this kind of stuff, and from Ingo. Now, at lower densities and higher temperatures, actually the situation is much easier because you can construct a model-independent description of the equation of state solely from the nucleon scattering phase shifts. And so Horitz and Schwenk described this in 2006. And so our model describes this as well. Of course, for dense neutron-rich matter, that's my favorite regime, because that's where neutron star observations really, as the ones I presented at the first part of this talk, really tell us about the equation of state. Finally, for the finite temperature corrections are difficult to do at high densities, but near the saturation density, different nuclear theory methods can be applied to help us understand what's going on at finite temperatures. And so we have constructed a model which properly describes all of these various experiments, observations, and theoretical developments, and then put them together. But and we have 9 tables which are on my website. You can download them and use them. But in addition to this, not only can we generate single equations of state, but this formalism, this open source code, and the paper, and the accompanying paper, describes a probability distribution of equations of state. So in practice, given enough supercomputing time, right, I could generate 1,000 equation of state tables, and we can do 1,000 merger simulations. And obviously, this is not yet possible, but we're moving towards the direction of trying to do uncertainty quantification. And I think understanding the uncertainties on the nuclear physics side is exactly one of the things that we need to do in order to do that effectively. And so you see, this is a probability distribution for the free energy per baryon at one particular density, electron fraction, and temperature. And you see, this is our probability distribution, and this is a couple different equation of state models. And one of the things you see is that the peak of this distribution has a little smaller values than some of the other equations of state out there. And this is in part because neutron star radius observations, like the constraints in the tidal deformability from LIGO, are pushing the radius down and pushing the pressure down, and thus pushing the free energy down as well. So I mentioned we have 9 equation of state tables, which are available now. And of course, as we've heard already several times this week, neutrino opacities are important in determining, we heard this morning from the electron fraction and our process abundances. So we need to propagate the uncertainties in the neutrino opacities in a way that's consistent with the underlying equation of state. And we're working on this with my postdoc Zidou Lin. So, and we're currently working on, core collapse simulations with these new equations of state, but I hope to see merger simulations with these new equation of state tables soon. And also we continue to make them better. And I think that process is important. We need to continue to advance the science. So another way of approaching, of solving this challenge of providing nuclear physics input to astronomy and using astronomical observations to understand nuclear physics is creating a community. And I'm really excited. We got $3 million from the NSF for a focused research hub called NP3M, which is centered at 5 institutions: the Syracuse, University of Houston, Indiana University, and Penn State. And did I say the University of Tennessee? I don't know. That's implicitly, of course, because this is where I'm from. But and one of the goals of NP3M is to understand the nuclear physics of multi-messenger mergers, to combine all of these different fields in order to in order to advance both the nuclear physics and the neutron star merger science. To that end, the NSF Focused Research Hub has allowed us to basically is just we fund postdocs. Okay, so our NP3M postdoctoral fellows, which we hired during our process last year, Peter Hammond, Zidou Lin, Konstantin Maslov, Rahul Somasundaram, and Lami Suleiman. I know I saw Peter here. I wouldn't be surprised if others have been here this week. And so we're really excited about NP3M and the things that it's going to do, what we're going to do with the NP3M fellows over the next year. And it's important also that we will be doing another job search in the fall for, I expect at least a few more NP3M fellows because we have the money for that. So, in the meantime, most of these, I think Rahul has begun, most of these NP3M fellows have not begun their positions yet. Lami is not joining us till April, for example, but I wanted to talk a little bit about the science that that these people are doing now, and sort of advertise. So I sent them messages. I don't think I didn't get any information from Peter, but that's my fault because I did this sort of at the last minute. So, but Peter is doing lots of excellent things in terms of viscosity and beta equilibrium. So I'm excited to hear more from him. But also we have Zidou Lin, who is, in addition to the error propagation for neutrino uncertainties or neutrino opacities, which I talked about earlier, Zidou is really connecting gravitational wave neutrino data to learning more things about what's going on in core collapse supernova, for example. And so we're, for example, using neutrinos as a probe of SASE. So really using neutrinos to understand what's going on inside, and possibly understanding the presence of a quark hadron phase transition. So I think that's a really, really cool way of connecting to the possibility for future data. Konstantin Maslov is working on the strong interaction side, extending phenomenological models both at 0 and finite temperature. I'm really excited in particular about the finite temperature. Konstantin is allowing us to connect the low temperature and high temperature communities on the nuclear theory side, which have traditionally been somewhat separate and used a little bit, use different tools. And so we're trying to really put these communities together, in particular because neutron star mergers, as you may likely have seen this week, achieve higher temperatures as large as 100 MeV in the center, and that demands different QCD, different strong interaction physics, not all of which we have really properly described yet. So Rahul Somasundaram has already started with Ingo Tez at Los Alamos, and Rahul is really our connection to sort of detailed QCD calculations from chiral effective theory, perturbative QCD, and so has already been working on this for a while. Finally, another one of our NP3M fellows, and Lami Suleiman, has been working, as many of us, on the equation of state and the connection to gravitational wave observations. But also, I'm particularly excited about what she's doing with at low densities with the crust. There's a lot of nuclear physics here which we don't understand, and so this is another accreting neutron stars is another data set, another class of objects from which we will be able to learn about, use with our combined inference to learn about what's going on with neutrons and protons in neutron stars. So I've gone quickly. My goal was kind of to give plenty of time for questions. and lots of time for discussion. So I think I've achieved that. I want to talk, just summarize. And so what are we doing? We're leveraging neutron star observations to learn about QCD and the nucleon-nucleon interaction. We obtain constraints on the mass radius curve in the equation of state. But as many authors have done, this is now a wide and diverse field. It's grown considerably since our initial works over a decade ago. But what I think is important about our particular work is we understand the approximate size and the physical origin of the uncertainties in our posterior distributions. And so being honest about these uncertainties, I think, is important, particularly as we get more data, because more data will constrain some things, but not other things. And we need to know how big these uncertainties are. I really believe that nuclear astrophysics needs multi-messenger astronomy to answer the questions that we are interested in. And of course, multi-messenger astronomy needs the nuclear physics input. I think neutron star cooling data is going to provide interesting exotic constraints on the composition of dense matter and maybe even on the neutron star radius. We have several new tables, which I'm excited to help you use. Please let me know if you. I'm continually working on both the open source code and the tables themselves. And eventually I hope to realize this dream of propagating these nuclear physics uncertainties all the way through to the mergers and maybe even to the R process abundances at the end. One of our tools is this new collaboration to NP3M, where we have hired fellows, and we're really excited about providing a good environment for our NP3M fellows, but also collaborating with all of you. So I look forward to doing that. And of course, there's an exciting future because more data is coming. Gravitational wave observations through either Cosmic Explorer or Einstein Telescope, nuclear physics experiments from EFRIB and other facilities around the world. PREX and CREX. CREX has an interesting recent paper. NICER, IXPE is now going, Astrobex, hopefully going soon. And there's a bunch of other things which I know I have omitted here, which are really important. So that's all I have for today. I'm happy to answer questions. Thank you very much for your patience.
Thank you, Andrew, for that excellent talk. Questions for Andrew? I see a lot of raised hands, so let's start with Sebastiano. I see you are muted, but I can't hear you. Can anyone hear him?
I cannot hear you, Sebastiano, yet.
Yeah, I still can't hear.
I don't know if he's not away from his keyboard. Sebastiano, you can type in chat. I can see it.
Yeah. In the meantime, maybe we can go to Yudi's question and then return to Sebastiano.
Okay. No, thanks for the talk. I wanted to clarify one point that I missed. You said that we do not know enough atomic physics in order to learn from the post-merger simulations and the gravitational wave signal in case we'll be able to see it. Or so I thought that we'll be able to use these observations to constrain the atomic physics or the equation of state, etc.
Yeah, so this is a good question. So this is sort of a chicken and egg problem, right? Because we need to know the nuclear physics to do the simulations to interpret the data, but we need the data to tell us the nuclear physics that we need to put in. So this is, I mean, basically we need to do everything all at once. And so this is a process. Obviously, we just continue developing everything in as much as we can. For example, we need to test a parameter on the nuclear physics side and see if it's important for the observations, and then go back and readjust our parameters. So this is sort of the quandary that we're in.
Let me put it this way. Assume that we'll have superb observations of the post-merger signal, and we'll have a suite of many simulations, each assuming something different about the nuclear physics. Will you be able to learn something from that?
Oh, sure. Yes.
Okay. Yeah, okay.
Yeah, definitely.
So it's not pointless to observe it and to try to simulate it, even though we do not know right now everything we need in order to simulate it correctly.
Oh, that's right. That's right.
Okay.
It's a very important point. Thank you.
All right, thanks.
Yeah, I just wanted to
I
add
see-
Sebastian's comment. Maybe you saw it too.
Our experience with the simulations is that the equation of state does not matter, but we do use a limited set of models. So I think it's important to characterize what the equation of state matters for and what it does not matter for. So I think, for example, it's been long said that the uncertainties in the equation of state do not impact the explosion mechanism for core collapse supernovae. Yes, this is true, but at the same time, they do impact the electron fraction for the neutrino-driven wind, our process. On the merger side, yeah, maybe they don't tell you detailed information about the kilonova, but maybe they do tell you, for example, the amount of mass ejected. This is something that Sekiguchi and others have found, I know. So I wouldn't say it's as simple as the equation of state does not matter. I would say the equation of state matters for some things and not others, and really understanding those connections are important. It would be yes, it's important to know which equation of state parameters are more relevant for gravitational waves. And so this is one of the things I hope to do, is provide an ensemble like these 9 equations of state that we can test. And of course, those 9 are chosen in an intelligent fashion, I hope, but we need to try to vary all the parameters which we think are important and do these tests. So yeah, these are excellent issues. I appreciate you bringing them up.
Next one is Julian.
Okay. I was intrigued by your brief remark about neutron superfluids, and 2 questions. One is, how well known is the phase diagram, just defining where and when there should be such a superfluid? And second, is the mass fraction of neutrons in the superfluid state large enough that it could have an impact on, for example, the internal rotation profile?
Yeah, so the phase diagram is not well known. It depends a little bit on what density and temperature you're thinking of. So traditional superfluidity, you think of Cooper pairs, a pair of fermions whose momentum is anti-aligned, so that the net momentum of the Cooper pair is 0. This is so-called singlet superfluidity. And so neutron singlet superfluidity dominates below the saturation density. The uncertainties in the critical temperature here are about a factor of 2. And so that's relatively well known.
And what is that
at higher
temperature?
that critical temperature. Sorry, ask that question again.
Oh, if it's known within a factor of 2, roughly what is that number?
Yeah, it's 1 MeV, right? So you expect, for example, that throughout a merger, that these neutrons are in the crust region are superfluid. Now, at higher densities, the pairing configuration that is preferred is so-called 3p2 or triplet pairing. And that critical temperature is likely to be less than 10 to the 9 Kelvin, but is uncertain by, I would say, maybe an order of magnitude. And at any, or more at any particular density. So again, I guess, no, I said it the opposite way, right? At 100 MeV, none of this superfluidity matters because we're above all the critical temperatures, right? So it doesn't impact the rotation properties. But if you're thinking about a cold neutron star, then all of these neutrons are superfluid and all of this matters. Does that partially answer your question?
Yes, thank you. And in terms of mergers, basically, it matters before the stars actually touch and there's serious shocks.
Yeah, right. Exactly.
Next, we have Stero.
Well, yeah, that's Stefan. Hi, Andrew. Very nice.
Hi.
I was just wondering, could you comment on the uncertainties in the thermal parts of the equations of state, and then maybe just a practical thing, how deep down in densities do your equations of state go?
Yeah, so the density range is between, I do this in this nuclear physics units of inverse cubic Fermi. So it's 10 to the minus 12 to 2.0. So that's from 10 times the saturation density to 10 to the minus 11 times the saturation density. So we go down to about, I think, 10 to the 3 grams per cubic centimeter. So it's quite a large density range. With regard to the uncertainty and the thermal effects, so the finite temperature properties we get from this nuclear theory calculations that Jeremy Holt does. So one of the things that we do is one of his parameters is the momentum cutoff for his momentum integrals in his chiral effective theory. And so we have 3 equation of state tables which vary this momentum cutoff between different values, 2 or 3. And so allow you to probe the uncertainties of the finite temperature effects. Now, one of the things that this formalism does not yet do, for example, is vary the finite temperature dependence of the nucleon effective mass. And so this is physics which has an imprint on the entropy at finite temperature. And so this is something that, for example, I think Darmstadt group, Achim Schwenk, and some other people whose names I can't remember. I know also that, yeah, there's a couple people who've worked on this whose names I can't remember off the top of my head. But yeah, this uncertainty is not yet in there. This is something we're looking at doing in the future.
Okay, thanks a lot.
Do we have any additional questions for Andrew? I don't see any questions in chat or any raised hands. So I guess we can just thank Andrew again for the very nice talk. And we can take a short break before reconvening at 11. I'm in a different time zone, so that's always confusing.